So, to do that what we will do, we will leave this example and go back to the Euler's equations of motion along the different directions. So, we have written the Euler's equation of motion along x, which is there in the board. Similar equations are there along y and z. Now, what we are interested to write or to find what is the difference in pressure between 2 points. So, let us say that we have 2 points 1 and 2 which are quite close, so that they are connected by a position vector dl. dl is given by dxi plus dyj plus dzk. Okay. So, this is the position vector that we are looking for. We are what is our interest? To find out what is the difference in pressure between points 1 to 2. So, whatever we did in the previous problem a bit more informally, we will now try to generalize it for a very general case, that what happens in that case. To do that, we will note that if you want to find out the difference in pressure between the 2 points, here pressure is a function of what? X, y and z. So, you can write this as the sum of these 3 partial derivative terms. Each of these terms we can substitute from each component of the equation of motion. So, the first term you can substitute from the x component of the equation of motion, which is written below. So, let us write that. So, this will be minus of, so this you are writing now the plus of this one. So, that means this term will become minus the right hand side. So, that will become minus of rho then plus a body force. So, plus rho bx dx. Dx with dx multiplication will come separately, we are just isolating the dp dx term. So, we are not writing the dx together with this. So, if you also consider the dx term together with this, then it will be the entire thing multiplied by dx. Now, we will try to write it in a compact form, because it is possible to utilize some of the very well known identities of vector calculus to simplify it. So, what we will do is we will write this particular term in a vector calculus notation. So, we can write this as v dot with gradient of u, right. So, then you will get these terms. Keeping that in mind, that other terms will also give similar expressions, like what will change for the second term, in place of this u it will be v, in place of this u it will be v, in place of bx it will be by, like that. So, it is very analogous, and we can write the general expression for dp as minus rho. Now, we will collect all the terms we will keep all the terms of similar type together. This is one term. Then next we will write that acceleration term, that is the convective component of the acceleration term. This is the temporal component, then minus rho and the body force term okay. So, these 3 types of terms are there, we will just for the writing convenience we will call it term 1, and there is a logic behind that. These terms are containing expressions of similar nature. So, we can simplify them in groups. Let us write or let us try to simplify terms 1, 2 and 3 separately. So, we will do that keeping in mind that the term 1 is the transient term, and when we are simplifying we will be keeping in mind that we will be utilizing the vector dl which connects the 2 points which are close to each other. So, the term 1 is minus rho. Now, can you write it in terms of the 2 vectors v and dl? Remember, v has components u, v, w, dl has components dx, dy, dz. So, if you write for example like this dot with dl, then that expression and this is the same, it is a dot product of this with this, of course you have a partial derivative of that one. So, it is just writing the same expression in a vector form. Let us write the term 2. How do you write the term 2? Minus rho, again let us try to write using the vectors v dot let us check whether this is alright or not. See, at the end we have to keep in mind that this is a scalar term, right. So, first of all whatever is a vector operator it should give back a scalar. So, you have one dot product and the dot product and the product of that is expected to give back a scalar. You can just check, let us check that. So, you can write this as v dot del then u dx plus v dy plus w dz. So, it becomes of the same form as that given by the term 2. Now, it is possible to simplify the v dot del v using a vector identity. What is that? So, v dot del v is equal to one important thing we will see that whether the bracket is to be put here or after the v, I mean still this is not complete. So, let us tentatively write it. This is a very well known vector identity. Now, you see that what is this v dot v is a scalar, the gradient operator operating on it makes it a vector. and this is very clear, this is a vector. So this should be a vector. So when you have v dot del, this is a scalar, but this being a vector, it keeps it a vector. So whenever you write an identity, these are certain common sense things that you should check, because depending on what you operate, the same thing may look may become a scalar and vector very easily, depending on how you put your cross products and the dot products. Now why we are putting in this particular form is because here you get the vorticity vector, and we were finding out that the condition of rotationality or irrotationality has some influence on the pressure difference between the points, and this vector solely is responsible for whether it is rotational or irrotational. Okay. So we will put that simplification here, we will put this as minus rho half in place of the curl of the velocity vector, we will write the vorticity, then dot dl. For the term 3, what we will assume, it is again a very general term, but we will assume that the gravity is the only body force which acts along the negative z direction, as we considered in the problem that we discussed just before this. So what we will assume that Bx is 0, By is 0 and Bz is minus g, because that is the common thing that we encounter in many problems. But if there are other components of body force, you know that how to simplify, like you can just put the corresponding components here. So then that will become term 3 will just become minus rho g dz. Since it has just only one scalar component, it is not useful to write it in a general vector form, it will not give us back many things. So dp is a sum of term 1, term 2 and term 3. We can simplify the term 2 and term 3 further. Let us try to simplify the term 2 one more step. So minus rho, let us now consider the dot product of this with dl. So half what is v dot v? V dot v is v square, where this capital V is the resultant velocity. So that we are writing this dot with this one, sorry, that is the first term, and you also have a term plus rho v cross vorticity vector dot dl. You can recognize that it is like a scalar triple product of 3 vectors, like A dot B cross C. Okay. So we will keep that simplification for a moment and just consider the first term. So what does the first term look like? Half that is the first term, I mean first term of the term 2, and then rho you can clearly see that the first term of the term 2 will become what? It is like it will become d dx of v square, is the sum of the 3 partial derivatives will give the total one. So, this will become at the end the simplified form minus half rho d of v square. So, this is like not d dx, just the total d. So, this is partial derivative with respect to x into dx, this is partial derivative of y into dy, and that with respect to z into dz. So, that is giving the total d plus the whatever term that is remaining. Now, let us put back all the terms together in the equation. So, what is our equation? Our equation is term 1 plus term 2 plus term 3 is equal to 0. That means minus rho that is the term 1. So, let us sorry dp not 0, it was dp. Then term 2, in place of term 2 we will write minus half rho dv square plus rho, maybe let us write dl dot v cross zeta, that is the term 2, and term 3 is minus rho g dz is equal to dp. This is a compact form and it is possible to simplify it even further based on certain special cases. So, what special cases we will be interested in, let us see. So, what special cases, maybe let us take all the terms in the same side. So, you have dp plus half rho dv square plus rho g dz. Up to this you can find some similarity with the Bernoulli's type of equation that you have encountered earlier, but you are getting also some 2 extra terms. Let us write those extra terms. So, plus then minus rho this equal to 0. Because these two terms are like beyond what you have encountered many times, we will try to put more attention on to the last two terms. We will put the first important attention on the last term, because this particular term in a case when it is a steady flow, this trivially goes away. So, there is no big controversy or there is no big uncertainty in that, that is quite understandable. But the last term, there are many possibilities when the last term can become 0. What are the cases? So, if you just write it in a determinant form, when you are having such a scalar triple product, you can write it in terms of determinants where each row of the determinant will represent the components of the vectors taken in the particular order. So, you have like dx, for dl you have dx dy dz, for v you have u v w, for the vorticity you have okay. Now, let us consider a case when this say rho 1, just look it into mathematically, say rho 1 is a scalar multiple of the rho 2. When it is possible? When the direction of dl and the direction of v are the same, then one will just be the scalar multiple of the other, because direction wise they are representing vectors oriented identically. So when that is possible, what is the special dl for which that is true? If it is located along a streamline. So if we consider this as like term A, so we will identify certain cases when A becomes 0. So A equal to 0 when certain cases, one is dl is along streamline, let us call the streamline direction as ds, S for streamwise coordinate. When that is the case, we do not care whether it is an irrotational flow or not, it does not matter whether it has components, non-zero components of the vorticity vector. Yes?
When it is streamline flow, then how can you say that
there is nothing called a streamline flow, first you have to understand, there is a streamline in a flow, there is nothing called streamline flow. Okay, next.
Sir, then how can you say that ds will be means multiple, ds divide dz will be multiple of,
This is what? This is the length element, this is the line element that you are considering. This is the component, these are the components of the velocity vector. What is the definition of a streamline? Such that tangent to the streamline at any point represents the direction of the velocity vector. So tangent is this direction, dl, a small elemental direction, and this is the velocity vector direction. So if they are located in the same direction, that means they are parallel vectors. That is the definition of the streamline, it is nothing extra. So dl is, if dl is located along a streamline, then we do not care whether it is a rotational or irrotational flow, but if it is not, then if the vorticity vector is identically equal to 0, then A will become 0, no matter whatever is like, no matter whether dl is located along the streamline or not. So vorticity vector is a null vector, this is irrotational flow. So you can clearly see that if it is a steady and irrotational flow, these two terms go away, and then sum of these three is 0, that means if you integrate that, the integration will give a constant of integration, and that is what we actually saw in the example, the problem that we discussed before going through this derivation. There is a third case, I mean there could be many such cases, but a third case, say you have the V cross this vorticity vector is perpendicular to dl. These two cases are more common cases that you encounter, this is not a very common case you encounter, but this mathematically you cannot rule out. You have a vorticity vector, you have a velocity vector, you can find the cross product and take an element in a direction which is oriented along that cross product, and then if you take such an element, then for such an element also for steady flow it will appear that the Bernoulli type of equation is valid. So this is not a Bernoulli type of equation, this is in fact one step before that, where we do not make any explicit assumption on how the rho or the density varies. So this is still the Euler equation of motion. So this is a more general way of writing the Euler equation of motion, where you are considering all the individual components and trying to write that in a vector form, but at least we can understand that this term becomes 0 under what cases. So let us say that we are considering one such case, let us say that we take an example, we are considering along a streamline. That is, what do we mean by along a streamline? That means we are interested to find out these changes. So see, this relates what? This relates change in pressure, change in velocity, change in elevation with respect to a change in position vector from point 1 to point 2. So when we are considering along a streamline, that means we are interested to evaluate that change by moving along a streamline. So never consider something like a streamline flow, again I am repeating, there is nothing called a streamline flow. In flow there are streamlines, but it is not a streamline flow. So when you have a streamline, we are looking for the difference in like these variables along a streamline. So when you have along a streamline, and let us say steady flow, as the first example. This is example 1. So then what you have, then a term will become 0, this term because of steadiness will become 0. So you have dp plus half rho dv square plus rho g dz equal to 0. This is known as Euler equation of motion along a streamline. Now this is valid both for compressible as well as incompressible flows. You are not yet committed of how the density changes. So now we are interested to see that how the density changes. To do that, we will let us say we will write it in this form dp by rho plus half dv square plus rho g dz and try to integrate it. Yes. So we will try to integrate it, the rho will not be there because rho we have already divided by rho. So when we try to integrate it, what are the points over which we are integrating? We are integrating with respect to 2 points 1 and 2 which are located on the same streamline, because we have considered along a streamline, that is we are considering this particular case which has made the term a equal to 0. So when we do that, this equal to 0, that is still valid for any type of flow, compressible or incompressible. Now you make an assumption that rho is a constant, assume that is a special case of an incompressible flow. So then what you can write, you can take the rho out of the derivatives. So you can write P2 minus P1 by rho plus half V2 square minus V1 square plus G into Z2 minus Z1 is equal to 0. Okay. This is nothing but the Bernoulli's equation, that is P1 by rho plus V1 square by 2 plus G Z1 is equal to P2 by rho plus V2 square by 2 plus G Z2. So it is like the it is in fact the Bernoulli's equation. Now you tell that what are the assumptions that we followed in deriving this. So this is the Bernoulli's equation. We will come into the physical significance of this Bernoulli's equation in the next lecture, but let us at least try to identify that what are the assumptions that we utilize to derive this. So what are the assumptions? So first start with the most basic assumption. When we wrote the equation of motion, what we assumed? Okay, only gravity is the only body force, it is okay, but it is like it is very explicit. What is not so explicit is inviscid flow. So inviscid flow is very important. Then steady flow, density is constant, it is a special case of incompressible flow, not irrotational flow. We have not taken this condition 3. When we take irrotational flow, we get a more freedom, then we need not be restricted along a streamline. But when we are considering along a streamline, then it need not be irrotational. If it is irrotational, fine, if it is not irrotational, still okay. So along a streamline, that is what we considered in this example, and in so these are the 4 ones that these are the 4 assumptions that we have considered in deriving this. Now these are the assumptions that we commonly use, because commonly we utilize the Bernoulli's equation along a streamline. At the same time, we must understand that these are not always the cases. Inviscid flow is the most important thing. Now can you tell that if you are thinking about Euler's equation along a streamline, out of these which assumption is not necessary? Say the Euler's equation of motion along a streamline, density equal to constant is not necessary. So density equal to constant is the additional assumption beyond the Euler's equation. Before, so after you make that assumption, you have to also keep in mind that I would say the most important assumption is inviscid flow, because many times we tend to apply the Bernoulli's equation in cases when viscous effects are very much present. Maybe many times you have solved such problems in your earlier high school exercise problems to solve like to get the velocity, pressure and so on. We will see that that is not fundamentally correct. In some cases you can get rid of that and still get some qualitative picture. We will see that when and when not, but fundamentally it has to be inviscid flow. Steady flow is for this version of the Bernoulli's equation, but you can also have an unsteady version of the Bernoulli's equation, that we will see later on, maybe in the next class, that where we retain this term and we can write a Bernoulli's equation by considering even the steady flow along a streamline, unsteady flow along a streamline. So only for this version it is steady flow, and that is the standard Bernoulli's equation, but we also have unsteady Bernoulli's equation. So for unsteady Bernoulli's equation the steady flow assumption is not required. Rho equal to constant is always required, because you are taking rho equal to constant and taking out of the integral, and along a streamline is required for this special case when you are not bothered about whether it is irrotational or not. If it is irrotational, then this need not be the case, so may be relaxed for irrotational flow. So what is the summary? The summary is, if it is an irrotational flow and other conditions are satisfied, that is inviscid, steady and rho equal to constant, you can write P by rho plus V square by 2 plus Gz is constant, need not always be along a streamline. So this is constant no matter whether you are considering the points 1 and 2 anywhere in the flow field, that is very important. So points 1 and 2 may be located anywhere in the flow field, still this equation is satisfied if it is an irrotational flow. If it is not an irrotational flow, then 1 and 2 have to be located along the same streamline. So these are very very important fundamental assumptions that go behind the Bernoulli's equation. We will stop here today, we will continue again in the next class. Thank you.